Good morning, everyone, and thank you for attending this session today. Today, we're talking about moving from interest to adoption of tire-derived aggregate in Alberta's transportation infrastructure. TDA, tire-derived aggregate, is not a new idea, but adoption of TDA often stalls between awareness and action. Our goal today is to focus on practical engineering applications supported by real projects, standards, and available resources. As you will see, TDA is an engineered product and have special properties that civil and geotechnical engineers need to solve everyday problems. My name is Bernie Mills, and I'm a senior principal in geotechnical engineering with Stantec based in Calgary. I've been involved in transportation projects using TDA since about 2006. My first TDA project was in New Brunswick for a highway project where we needed a large volume of lightweight TDA fill to solve a large embankment failure that occurred in soft marine clay. Since the New Brunswick project, I have designed other highway embankments and roadway infrastructure projects using TDA in Nova Scotia, Saskatchewan, and more recently in Alberta. And I'm pleased to be able to share some of the things that I've learned along the way. So our agenda for today, we're going to start with a description of what TDA is and how TDA is produced. Then we're going to review some of the engineering properties and then the ASTM practice standards. We're going to look at transportation applications, benefits, and case studies. And then we're going to close with some key considerations and available resources and support. The intent is to give you enough information so that you can evaluate if TDA is potentially right for any of your upcoming projects. What is TDA? TDA is an engineered performance-based aggregate made from recycled tires. This versatile material is used to provide lightweight, free-draining, and durable solutions in numerous civil and environmental applications. TDA is manufactured by shredding end-of-life tires into smaller pieces, typically ranging from 25 millimeters or an inch to 300 millimeters a foot long, and screening and separating the shreds into different sizes for different uses. The final TDA product is then subject to quality control testing to verify its engineering properties and compliance with ASTM standards. The engineering properties of TDA play a crucial role in determining its suitability and performance in various applications. Understanding these properties helps engineers and project managers select, design, and construct with TDA. Key considerations that are included are geotechnical, environmental, dynamic, and thermal characteristics, each of which affects field performance in different ways. Tire-derived aggregate helps solve a variety of engineering problems, making it a smart alternative to traditional aggregates. TDA has low unit weight compared to conventional soil. TDA is about a half to a third the unit weight of soil. This makes it great for embankments, bridge approaches, and slope stabilization projects. Due to its low unit weight, TDA is ideal for retaining wall backfills. With high porosity, TDA drains water up to 10 times faster than gravel, making it ideal for stormwater systems, drainage layers, and preventing water damage. Based on the ASTM standards, TDA have negligible offsite effects on water quality. TDA exhibits low thermal conductivity compared to conventional soils, so it is an excellent insulator. Several studies have demonstrated the effectiveness of TDA to attenuate vibrations. Any self-heating behavior of TDA is controlled by following and adhering to the ASTM specifications and standards. So when we talk about using TDA in engineering, the most important technical reference is the TDA practice standard, ASTM D6270. So for unconventional materials like TDA, having a recognized standard turns it from an experimental idea into an engineered practice. This ASTM standard covers the full life cycle of the material. It addresses testing physical properties, design considerations, construction practices, and environmental evaluation, including leachate potential. Importantly, it's a guidance standard, not a prescriptive specification. It helps engineers apply judgment rather than forcing fixed rules. The standard explains how to evaluate TDA's engineering properties using adapted geotechnical testing methods. It also emphasizes that TDA behaves differently from mineral aggregate, so testing and design approaches must account for that. It also outlines practical construction guidance, handling, placement, confinement, inspection, and finally, quality control. The biggest value of this ASTM standard is that it gives engineers and regulators a shared technical reference that helps create consistency in design, reduces uncertainty in approvals, and supports defensible engineering decisions. With greater awareness and adoption, the ASTM standard can help transition TDA from being seen as an experimental option to a mainstream geotechnical and civil engineering material. So what are some of the TDA applications? TDA is not a new concept. It has been used widely and successfully across Canada and internationally for decades. In transportation projects, TDA is typically used where its lightweight, drainage, and flexible properties solve specific infrastructure challenges. One of the most common uses of TDA is lightweight embankment fill, where the lower unit weight helps reduce stress in weak soils and limits settlements. It can also be used in roadway subgrade systems, where its free draining structure and thermal behavior help manage moisture and reduce frost-related movements. Behind retaining walls and bridge abutments, the lower density reduces earth pressures, while its permeability helps prevent water buildup. Because it's highly permeable, TDA also works well in drainage layers, such as edge drains or French drains. And in some rail or light rail environments or heavy traffic corridors, TDA's flexibility can also help absorb vibrations. So what are some of the benefits of TDA? So when properly specified and constructed, its material characteristics may result in cost, schedule, constructability, maintenance, and long-term performance benefits for the project. TDA often reduces the overall project cost, especially when the beneficial properties are required. TDA's lightweight, free draining, and adaptable characteristics can improve constructability by expanding workable site conditions. Successful projects lead to economic, social, and environmental benefits as well. Greater value for money, taxpayer savings or more infrastructure is built, locally sourced material support employment, strengthens the economy, build capacity and sustainable design and construction, and reduced environmental footprint. We're now going to look at several TDA case studies in the transportation industry. These examples span different climates, soil conditions, and applications, and many include long-term monitoring data. So this first project case study that I'm going to share is the St. Stephen Route 1 highway embankment failure repair in New Brunswick. This is my first TDA project that was completed in 2007. This project involved repairing a major highway embankment failure that occurred during construction over soft marine clay. The photo on the top right shows the deep-seated failure that occurred. And because of this big failure on marine clay, we needed lightweight fill. So reducing embankment weight became the controlling design requirement. Lightweight TDA was the solution in combination with stage construction and geotechnical instrumentation. This project was the first TDA project in Atlantic Canada and the largest TDA project in Canada at the time. And at the time, it was the second largest in North America. We used 1.4 million end-of-use tires to construct this project. This project is an especially important case study in the industry because it's been monitored and continues to be monitored after 19 years. And the embankment, the highway, continues to perform to this day. The project achieved significant cost savings as compared to the other options explored at the time. And this project also won the Association of Canadian Engineering Companies New Brunswick Award of Innovation in 2010. The second example is a new highway construction project. And this is another project that I worked on. It was for Highway 39 near Regina. And this was completed in 2022, so fairly recent. This project involved constructing a new highway embankment using TDA over an existing dugout. TDA was delivered, placed, and compacted using conventional earth-moving equipment, as shown in the top right photo. This project was built as a demonstration project with instrumentation and has shown good performance under service conditions. The bottom photo shows the completed surface of the highway. This third example is an Alberta rural gravel road repair application. So Alberta also has a significant history of successfully using TDA for road building. In 2012, ARMA collaborated with the County of Stettler to use TDA as lightweight fill in place of conventional clay. The project involved construction of an embankment for a section of Range Road 184, located 40 kilometers southeast of Stettler. The project used 3,600 tons of TDA in a 1.6 kilometer rural road section. Adjacent land consisted of low-lying pasture and a seasonal slough, creating wet conditions typical of areas where subgrade performance and embankment stability can be challenging. This also represented the first test of TDA made from off-the-road tires in our province. The objective of this project was to evaluate the feasibility of using TDA as fill for road embankments in terms of both constructability and long-term performance. So following completion, a review was conducted, and it was observed that the TDA resulted in a less rigid fill that still provided the required strength and behavior. Going on to our fourth case study, this is the Alberta TDA test road embankment. In 2012, ARMA went further in testing the use of TDA on a high-volume paved road. ARMA formed an innovative partnership with the University of Alberta, Alberta Transportation, the City of Edmonton, and the Canadian Foundation for Innovation to found the Integrated Road Research Facility, or IRRF. The IRRF includes a fully instrumented test road located approximately 15 kilometers east of Edmonton, of downtown Edmonton. The test road is still unique in Canada, and more than 8,000 tons of recycled tires were used in this construction project. It was also instrumented with more than 250 pavement and geotechnical instruments during construction. This geotechnical instrumentation was used to monitor the TDA section's compression behavior, internal temperature, and drainage characteristics. Findings indicated that TDA performed as well or better than the control section. The road is now more than halfway through its service life and remains maintenance-free, and no performance issues have been identified. Moving on to our next case study here. This is a Manitoba TDA roadway pavement repair application. Manitoba is one of the most challenging environments in Canada for road durability. The combination of extreme freeze-thaw cycles, high groundwater, poor drainage, and frost-susceptible soils creates ideal conditions for frost heave. In many communities, this can mean the same roads need repair year after year. Manitoba has been using TDA in municipal road repairs since 1998, and over more than 2 decades, it has become a proven tool for stabilizing frost-damaged roads across the province. TDA works well in these roads because it's highly permeable, so it allows water to drain quickly instead of becoming trapped under the pavements. It acts as a thermal insulation layer, reducing the freezing depth and limiting frost lensing formation. And it's lightweight and flexible, and as such, it tolerates seasonal ground movements better than rigid mineral soils like gravels. Municipalities report that sections of road repaired using TDA have stayed smooth for years. Importantly, these repaired sections show little to no recurrence of frost lensing damage. This isn't just short-term success, it reflects long-term performance in one of Canada's harshest climates. Importantly, Manitoba's TDA repair program provides significant savings to municipalities as it helps to break the cycle of repeated frost repairs, reducing ongoing maintenance costs by addressing the problem at its source. Brett Eckstein, the CEO of Tire Stewardship Manitoba, has gone so far as to say, as one program lead in Manitoba put it, there hasn't been a soft road that TDA couldn't permanently fix. Our last case study here comes from California, where TDA was used to attenuate vibrations in the light rail transit industry. In this light rail project, TDA was used beneath the track to attenuate vibrations. It provided effective vibration control using conventional construction methods at a significantly lower cost than alternative mitigation systems. Successful TDA performance depends on proper design and construction. This section shifts from case study examples to how to apply it correctly in the field. When to consider TDA on your projects. Consistent with ASTM guidance, the following considerations are intended to help identify project conditions where TDA may provide engineering advantages. So when you have projects or sites where we have weak or compressible soils that require lightweight fill. Another example is earth pressures are a controlling factor. Another one is drainage applications where they're critical to long-term performance. Freeze thaw or frost penetration that drives maintenance risks. And last but not least, the repeated loading, vibration, and cyclic loading where those loadings are expected. It is important to note that TDA often solves multiple issues or problems on projects. An example is where you need both a lightweight fill and good drainage, which is relatively common in Alberta roadways and highways and slope stabilization projects. What are some project considerations? When using TDA, construction practices matter just as much as design. It is a huge advantage the fact that TDA can be handled and transported using conventional equipment, such as floating floor trailers or side dump trucks, as shown in the photo. TDA can also be placed and compacted using conventional earth-moving equipment, such as dozers and loaders, and compacted using smooth drum rollers. Proper material handling, control lift thickness, confinement, separation with geotextiles, interface protection, and inspection and quality control are all key to successful performance. Thank you so much.